Hello to everyone. My name is Luis Valencia, and in this presentation, I'm going to talk about the oxygen minimum zone variability at the Juan Fernandez Ridge with an emphasis on the role of mixing processes and the influences of mesoscale eddies. At subsurface depths, zones with low dissolved oxygen concentrations are seen at the eastern boundary of welling systems and at the northern part of the Indian Ocean, seen in this figure by the black contours. At the eastern Pacific, Arabian Sea, and Bay of Bengal, these low oxygen concentrations reach values below 0.5 milliliters per liter, owed to the presence of an oxygen minimum zone, characterized by these extremely low dissolved oxygen concentrations, shown here by the red dashed contour. Particularly, the eastern South Pacific presents one of the widest oxygen minimum zones, and is related to equatorial subsurface waters, which also have higher salinity and nutrient content. Near the continental margin, this water mass is transported poleward by the Peru-Chile undercurrent, so the variability of the poleward extension of the eastern South Pacific oxygen minimum zone is dominated by its variability. However, at open ocean, there is a lack of observational data to assess the different scales of variability of the offshore extension of this water mass and hence of its oxygen minimum zone. Recent studies based on an hydrodynamical biogeochemical couple model suggest that planetary waves and intrathermocline eddies, a type of subsurface mesoscale eddy, had a significant role on the seasonal variability of it. Of central Chile, the western boundary of the oxygen minimum zone interacts with the Juan Fernandez Ridge, a chain of topographical elevations over the seabed. The Juan Fernandez Ridge has 22 summits, with 8 of them reaching or crossing this low oxygen region, with 6 tall seamounts and 2 islands, Alejandro Selkirk at west and Robinson Crusoe Islands at east. These seamounts and islands are known as endemic hotspots, and due to the fragility of their marine ecosystems, they were recently declared as marine protected areas. Remote sensing and modeling studies suggest that primary productivity around the easternmost island of the Juan Fernandez Ridge, Robinson Crusoe, has a significant influence of water of coastal origin through the strong mesoscale activity of the region, and that submesoscale variability related to von Karman vortexes can locally increase it. But is this mesoscale and submesoscale variability reflected in the variability of the oxygen minimum zone over the Juan Fernandez Ridge? It is also known that sea-bottom irregularities such as ridges, seamounts, and islands promote a local enhancement on diapycnal mixing, mostly related to turbulent processes. So, how strong is the diapycnal mixing and diapycnal fluxes of dissolved oxygen over there? And if mesoscale variability modulates stratification of the water column, can it also modulate diapycnal mixing intensity? To answer these questions, we used information gathered during an oceanographic cruise in September 2015, consisting in a high-resolution CTDEO sampling over 4 of the tallest seamounts of the ridge, accompanied by microstructure measurements on each of its summits, and a control station located 30 kilometers south of each seamount. Only the information associated to the seamounts located at the western tip of the oxygen minimum zone was used, associated to Dresden, Sinkeport, and Duke seamounts. Also, on the slope of Robinson Crusoe Island, at the beginning of the survey, a mooring with 2 ADCP and 3 microcats was deployed, recording currents and CTDO information for approximately 9 months. According to the World Ocean Atlas climatology, during September, late winter conditions, the oxygen minimum zone, depicted by the 1 milliliter per liter isoline, is close to the coast and exhibit a poleward narrowing, with its western limit associated to concentrations of 1.5 to 2 milliliters per liter reaching the Juan Fernandez Ridge. In the vicinity of the ridge, denoted by these polygons over here, stronger variations in temperature salinity, and dissolved oxygen are seen at the subsurface strata associated to the oxygen minimum zone. These changes in the water column properties tend to follow the large-scale features of the water masses at these depths, with increasing dissolved oxygen content and a lesser participation of equatorial subsurface waters to southwest. But as we can see on the control stations of Dresden and Cinque Port's Duke seamounts, showed here by these stars, some opposite anomalies appears with higher content of equatorial subsurface waters and a stronger oxygen minimum zone. So what would cause these anomalies? During the entire sampling period, a mesoscale anticyclonic eddy was located southwest of Dresden seamount. So we can see here the evolution of that eddy. But as seen on these relative vorticity charts, its influence extends to Cinque Port seamount and to a lesser extent to Duke seamount, with these last two also influenced by a cyclonic eddy located north of them. This anticyclonic vortex corresponds to a long-lived anticyclonic eddy formed off the coast of southern central Chile. According to its features, it corresponds to an intrathermocline eddy, concluding that the stronger oxygen minimum zone seen on September 2015 was due to the equatorial subsurface waters carried by this eddy in its core. Mesoscale structures are continuously impinging the Juan Fernandez Ridge, and this mesoscale variability is reflected in its oxygen minimum zone. Changes in the equatorial subsurface water content at subsurface level not only affect this low oxygen concentration, they also promote significant changes in stratification of the water column, being more acute those associated to mesoscale variability of 1 to 2 standard deviations. Correlations between relative vorticity and vertical density differences. Relative vorticity time series is depicted here by the continuous black line. Capture the effect of mesoscale eddies, with a stronger stratification when the area is dominated by anticyclonic vorticity and reduced values when cyclonic vorticity is present. Considering these low frequency changes in stratification and the scale of the physical processes that could enhance turbulent diapinal mixing in a region such as this, mesoscale modulations on its intensity are expected. During the late winter survey, this modulation was also evident, with a decrease in stratification as we move away from the intrathermocline eddy and get closer to the cyclonic one. Here the stratification values are depicted by these triangles. These spatial changes are also depicted by the dissolved oxygen concentrations, with an increase of oxygen content in the same direction. Comparing the values of turbulent dissipation, diapinal diffusivities, and dissolved oxygen fluxes, the effect of topography is evident, with higher magnitudes near the summits of the tallest seamounts, Dresden and Cinque Ports, depicted here by the black lines, and away from the intrathermocline eddy, where stratification is lower. Our main conclusions are that mesoscale structures in the form of meandering currents, filaments, and eddies are the main forcing mechanisms of the Juan Fernandez Ridge oxygen minimum zone variability, with its intensity mostly driven by the arrival of intrathermocline eddies. Mesoscale modulations are also present in the stratification and in the intensity of the diapinal mixing, thus in the ventilation of the Juan Fernandez Ridge oxygen minimum zone, with the last also enhanced in the tallest study seamounts, Dresden and Cinque Port. To understand how endemic marine ecosystems are coupled with these dynamics, future studies using in situ data and numerical simulations that adequately incorporate realistic diffusivity coefficients, such as the obtained in this study, are needed. Thank you.